So hello, this is a Haskell tutorial, and this episode is on functors, doing a little series on the more difficult aspects of the category theory parts of Haskell. So this is from the perspective of somebody, this is given from the perspective of somebody who's learning Haskell and didn't get it the first time round. I didn't really find anything good on the internet. There probably is, but I thought this might help others and it might help me. So I am not a Haskell expert, but I have been learning Haskell and I come from an object-oriented programming background. So if you're a bit close to me, then that might help you a little bit. So without further ado, let's go through this. So actually let's put the pointer on. So this tutorial assumes you have a basic knowledge and the syntax of Haskell, but even if you don't, you might be able to just about get through. So I'll start off with a quick explanation of what a functor is and why you might want to know, and how to identify one a little bit. So then I'll go through the following functors, how they're implemented and used, maybe list functors, and the laws a functor must adhere to. Actually, it's not in that order, but that's fine. So, okay. So functors, monoids, applicatives, monads. They are horrible names. They don't describe what they are. So how I see these, and I think this is how they should be seen, they are just common patterns in programming. And the idea is that if you understand these patterns, you'll be able to identify them and apply techniques that are applicable to those patterns all over the place. So these are really broad generalizations, and so we want code use, loose coupling, cohesion, don't repeat yourself. They're all best principles. So identifying these patterns and applying techniques that are relevant to them are some of the ways in which we can achieve those results more easily. Now we're going to start with functors, just because it's used elsewhere. It's used in applicative functors. So again, why do we want to know about these things? Why do we want to know about functors? So Scott Vlashin, he said something along the lines of, this isn't word for word, functional programmers spend their time linking and piecing together functions so they fit. They do composition all the time, composing functions. So identifying the patterns above, they allow you to compose the pieces of your program a little bit more easily. So here is the, before I get into functors, I just need to do, I think this is the last slide before we get into functors, just a little bit. We use a little bit of background on what we're going to be using. So maybe is a data type, and this is the maybe data type definition with its constructors, and we're going to be using maybe. I think it's quite a good example when you come to a lot of these. So just in case you don't know what a maybe is a data type that has either nothing in it or a value. So we show this by having actually nothing. These are two constructors, and so if I do nothing, just 5, so that's a maybe type of an int that holds the value 5. So if I do type in Haskell, as you can see, here it's a maybe type of a, and a is a number, so it's a number actually, it's not an integer. And so maybe types can be used to identify or to hold data where you might have some data or you might not have some data, and be very explicit in those two different scenarios. So you say you have a customer, you go to the database, you return the customer. If he exists, you get nothing back, and if he exists, you get a customer of type you get a maybe type of just a, so you get a customer there. Okay, so what is a functor? The most basic explanation is it's a type that can be mapped over. So you've got your thing, your type, can you map over it? Can you map it? Yes, you can. So it is probably a functor. So lists are functors because you can map them. So if I do map, and if I do +1, that's shorthand for there. So I'll write it out explicitly this time. So this is a function that takes a value, adds 1 to it, and as you can see, that does indeed map 1 to it. So lists are functions, and each element of that list is the value. So a maybe type, can you map over a maybe type? Well, it does come with its own map function, and so mapping just takes the value and adds 1 to it. Yes, you can. So mapping allows you to apply a function to the value inside a type. It says this value as the parameter, do the work, return it, and then recreate it. So then you get just 6. And in Haskell, if you have a functor, you define the implementation for the functor, and that definition comes from a type class. This is the functor type class definition of a functor. So this is a lot like an interface, really. So it doesn't define any behaviour, but it shows you what it should do. So we have a function here called offmap. You pass it, this is a function name called offmap. You pass it a function that takes value a, say that's int, and returns value b, so that's toString. So this could be an int toString function. And you have your functor, so this is the item in a list, for example, and you pass it your value. So here you pass it 1, 2, 3, whereas 1, 2, 3 will be your elements, and the functor will be your list. And then that creates a new functor, and those functors will be turned into strings b. So that's a functor type class definition. And so this is the implementation of the Functor type class for maybe. So this instance, I call it implementation because it's a little bit more like object oriented, but this implementation is what defines the behaviour of a functor. This says, I can map, I am a functor, you can treat me like a functor. So for maybe, what we do, we have our fmap name, this function name. So let's just do this in the console, fmap, and then we have our function that we pass in. So we go +1, and then we have our functor, which is our justify value. The dollar is just brackets around here, that's all that means. And what that does, it says take my f value, take my x value, take my functor, take my 5, and then use my 5 as the value for my function, and then recreate my functor. So, and the same here, and so if it doesn't have a value, it makes no sense to apply that function, and that's what we're saying in this scenario here. So this is pattern matching. So if it matches the just, we do this branch, and if we match nothing, we do this branch. If it doesn't have a value, there's no point in trying to do something silly, so we just return nothing. So let's just do that again. What's +1 to nothing? It's nothing. Okay. So here we see that broken down again. We do fmap plus x plus 5. So let's break this down again just to see what this happens. So we do fmap function our just with maybe value. It matches the just branch. So we do this. We feed our value of our functor into our function, and then we recreate our functor. So we've got our to value here, and we've got our function here. Our to value goes into the function. We evaluate the expression in our function, which is 2 plus 5 is equal to 7. Then we recreate our functor, and we get just 7. So it's very much like this whole mapping business is very much like I have a value in some kind of container and I want to apply a function to it, and it's got to be a one parameter function if you want to get a value out. So there we go. So how do you identify functors? And well, there are a number of rules. There are two rules or laws. There are two laws that, if satisfied, mean that you have a functor. So the first one is fmap id functor. So id function, the id function is just that. So you return, it's a one parameter function that returns exactly that one parameter, unmodified. So you give it 5, it returns 5. You give it hello, it returns hello. So it doesn't do anything at all. And if it satisfies that, that's one rule. And we're halfway there to getting a functor. Okay, so if you map your functor over ID, you should get back exactly what you were given. So we have fmap here, we have our ID function here, we have our functor here. So as you can see, value in, function in, value goes in, it gets evaluated to 3, ID 3 is 3, and then we recreate our functor using just. And so that's it really. So that's one of the laws. The other law, so actually let's just go back to the other one. Now really what this is saying is that this function here must be pure, and this constructor must be pure, and it mustn't have any strange values hidden in there that get updated in strange ways that you can't just recreate by calling its constructor with the value. So if you've got this value and you have your constructor, well, you always get the same result with your value and your constructor, and that is effectively what this rule says. And really the second rule, and we only have 2 rules for functors, is pretty much the same. It's a little bit more difficult in terms of understanding, but we'll try and go through it. So the rule is, when you compose 2 functions, then map the resulting function over a functor. You compose 2 functions. We have our 2 functions here, +1 and +2. So we've got our variable x. We've got 1, that returns a value. Then we add 2 to it. We still have our x going in, so that's x plus 3. That part there. So that's our composing our 2 functions. Then mapping the resulting function over a functor. So we've got our resulting function over a functor. So it's just the same, fmap plus 3, just 5, we get just 8. So that there must equal the other side of this. So this is quite simple as well. So think of this part on its own. So this is exactly what we've been dealing with. Fmap plus 2, just 5. So this will return a functor. 5 plus 2 is 7. So, and we get just 7 out of here. So let's just do that actually. It's a bit easier to look at. Fmap plus 2 just 5. We get just 7. So that's one side of this expression here. Then if we do fmap plus 1, just 7. I forgot the dollar. That will return just 8, which is the same as up here. So in this instance, our maybe type and the definition of its functor satisfy the 2 laws. And it just condensed, the law is fmap, our 2 functions composed should equal function 1, yeah, this fmap function 2, fmap function 1 composed together. So just imagine that there's a functor there and functor there. It's the same as this example here. Okay, so now the way I read mapping, because functors, defining functors, and what you get from having a functor and identifying a functor is you get the ability to use map. So if you identify what a functor is, it's a single value in a container, then you can map on everything. And sometimes I used to have a tiny little bit of difficulty reading the mapping function. It's okay on this because I'm used to it, but things like maybes. So we have our container, we have our value. Our value is the parameter to our function. We evaluate it, 5 plus 2 is equal to 7, and then we recreate using our constructor the functor, and we get just 7. So that's how to read it. So the value is the parameter to the function, and then we recreate our function using that new value. So another functor, this is kind of how you start, oh yeah, that's also a functor, so I can map it. So IO action in Haskell is also a functor. So you have instance functor IO where. So this is the definition of, this is the implementation of a functor for IO action. So fmap, our name, our function, the action. So the action could be get line. Can I do this is going to be a bit experimental. Okay. So, and our action be just, I think it's just get line. Yeah, that's right. Okay, so let's just run that again. So it's just that on the screen. So fmap, function, IO action, get line is an IO action. And so what happens in here? Action gets evaluated, and the result of action is put into a variable. The variable is the parameter to our function that we passed in, so blah. Oh, actually that's hell blah. So let's just concatenate our parameter with blah, so that forms hell blah, and return is not what it is in C# and other object-oriented languages. Return is a function that puts a value in the context of an IO type. So we'll come to that a bit later, but return is not a keyword. Return is a function, and that function just wraps our value and says now we've got an IO result, similar to getLine. So let's do okay, here we go. So this is exactly what I wrote down here. Similar anyway. So if we do fmap reverse, so it doesn't need any parameters. GetLine hello, it just reverses it. So again, the value of our getLine is kind of our functor, our functor, because it's an IO. IO is our functor. That is parameter for our function, and then we return our value after we have evaluated our function, and then we wrap it in IO. So we wrap it in our functor. we get IO ole back. So okay, another type of functor is one parameter functions are functors. So all one parameter functions in Haskell are functors, and all functions in Haskell are one parameter functions, so all functions are functors. So just a little note on how to read this. This is the implementation of Functor type class for functions, and so this arrow R, that I'll show you how to read that here. So we have our parameter, result of our function, and the function definition. So this here is a type of value operator, like star for multiply, add for addition, and this just says that we have a function. And to put this into infix operator, this is an infix operator, sorry, to put this into prefix, as a prefix operator, we just wrap it in brackets. As you can see here, this is exactly the same. Parameter A, return parameter B. Now, if we just want to match on our input, our function, we just leave out the B, which is exactly what this is. This just says our parameter and our function is a functor. So the definition is we have our fmap, we have our function that we want to apply to our functor, and G is actually a function, so we apply a function to a function. How does this work? We have our function, say this is +1, and this is our functor, this is part of our functor, this is the value of our functor, this is +1 part of it, the other part of it is the parameter, and so this is a parameter of our function, so this is like the constructor, and this is like our value, and we apply our function to it, and we apply our parameter to our function, and then we apply our function of our fmap, we map it, we map the results of our function here. This one's a bit easier with an example, so let's make that a bit better. So this is a definition again. So if we have fmap a ×3 function, so that's parameter, what we give it, be an int, so 5 times 3. And our other function, because this function is our functor this time, a +5 function. So let's replace these values. +5 is our value of our functor, times 3 is our function with passed in, and this is our constructor. This is our function part. So functions are functors, so this is a functor and this is the constructor for that functor. So that's okay. And so let's actually just give it value. Actually, first of all, what I'll do, this mapping class returns a function. As you can see, it returns a function that takes one parameter and returns a value of the same type. So if I give it a value, there we are. So what happened there? So our value came in as our parameter. This is our value. I should give them the same value actually. That would be better for this example. So our value is added to the 5. Value 8, that's 12. 12 is passed into our multiply 3 function. That returns 36. Great. Okay, so again, the functor is for parameter to the function here, and the constructor is for one parameter function. So this is our constructor. I think this is a little, yeah, you can see it this way. So the function, the constructor is the one parameter function. And actually this is the value. I'll skip over that, that's not very clear. Okay, so here we go. Here's a little bit more of a complex example. So we do fmap. This is a 2 parameter function that we're passing in here. And what's the type of that? You might ask. Oops. Need a space. Oops. It wasn't that. That's what I was doing wrong. So colon t multiplied by 4, and so this returns a function. So that returns another function. So a function here, parameter, returns another function that takes another parameter. So if you pass 2 parameters to this, you'll get your result. So let's do that. We get 16, which is the same here. So let's just walk you through this one. So this is our definition of, this is the implementation of our fmap function here, this part here. So we have our function for our fmap, and we have our value for our functor, which happens to be a multiplied by 4 function, just without its parameter. The parameter we move over here. The parameter is the constructor, and we apply that to it. And then, so as you can see, this will require one parameter. This will be evaluated, and it will partially apply this 2 parameter function, and that will return on the function. So here we go. So we take our 3, we pass that in. So the 3 times 4 function with the 3 breaks down to 12. Partially applied, we have our plus 12 function. We give that the value 4, and we get 16 back. So, okay. So, a quick summary. Functors are values that permit a mapping whilst adhering to the 2 functor laws, which the 2 functor laws basically declare purity in the constructor and the type. and the functor type class declares in Haskell. The functor type class declares what is and what is not a functor in Haskell. So it could adhere to those laws, could look a lot like a functor, but it won't behave like a functor in Haskell because we don't actually apply the type class of functor to it. So the type class of functor is slightly separate to what a functor is. This is the declaration. This is you, or the system, Haskell, saying this is a functor. So the fmap function, that defines the behaviour of that mapping. So we could actually put the behaviour slightly differently. But in the examples we've looked at, we haven't. We've only had one behaviour for each type, but we could actually have two different behaviours for a functor for fmap. So the way I see mapping is the value is the parameter of the function that you pass in, and then it's recreated using the constructor. Now the behaviour of fmap can differ between functors, as I was saying there. It's just a mapping function, so you can map it in different ways. And we looked at the implementations of maybe IO lists, function, functors, and that's about it. So thank you very much, I hope that was useful, and I hope to do a video on monads, monoids, applicatives, and maybe something else. We'll see. Thank you very much.